Good afternoon, everyone. Welcome to today's webinar. Today's webinar topic is Introduction to Weld Fatigue and FE-safe VERITY. Here is a outline. We will start with the introduction and background. Then I will take VERITY structure stress method, which we will know what stress and what is the stress we need to take for the fatigue analysis, and which is the ascent curve which we need to consider, and so on. And afterwards we will study in brief regarding master ascent curve approach. Then we will also see the development of a simplified procedure for spot welds. This is a fatigue analysis process. By now, I think you're all familiar with this flow chart. This is a diagram of a design workflow involving fatigue, and this is the same workflow for fatigue analysis of welded structure also. Designer will pass the design onto the design engineer or FE engineer to do the FE analysis. Then FE-safe takes the stresses and strain from the FEA software, combines it with the loading history and material data. Then FE-safe will give a fatigue life prediction. The result can be viewed in your FE software as a contour plot. And based on these design, based on these results, you can do your redesign, or you can sign off for your testing. FE-safe also support all the major FE codes. You can see that on screen. First of all, if you look at a loaded joint, in this case, a simple T-weld example I have given. You're trying to perform the stress calculation and life prediction. You will face a couple of problems. One is that you will have a stress singularity in the sharp notches. In this case, the toe of the weld you can see with the red dot on it. And you will also have a complex stress distribution arising from the surface through the thickness of the plate. And when you are applying finite element analysis and try to assess the stresses, you will run into mesh sensitivity problem also. Different codes and standards based on this nominal stress or extrapolation based hotspot stress method will struggle significantly for getting the right answers. One more example I'd like to point out is the fact that depending on when you mesh your finite element model and you choose to pick something like a normalized stress, and depending on the size of your mesh, your normalized stress will be completely off the chart. So this is one more reason why this approach will not work. As I mentioned, there is a method called hotspot stress method, which is not suggested. What this is essentially, what this does essentially is it assumes that stress is at a certain distance away from the weld toe, and using a second support point a little closer to the weld, it can be used to extrapolate a certain stress, which can be used to calculate the stress concentration factor. There are few extrapolation procedures available, and the one that we see here in the left is a standardized one. Okay. you look at 0.4 times the thickness distance and 1 times the thickness distance away from the toe. So what does this mean? Let us understand. In this case, we have a plate thickness of say 15 mm. Okay, and it will be there will be two different points. One will be at 15 mm and other will be at 6 mm because of this 0.4 t by 1 t calculation. 0.4 t is nothing but 6 mm and 1 t is nothing but 15 mm. So we have 2 points. So we can connect these two dots with a line, and if we refer the diagram, we will find out the stress concentration factors, and we can read out these values as you can see. The problem, as you can see here, if you look at different procedure, neither procedure creates an identical value for the stress concentration factor. Not only that, but there is a intense scatter. This is one reason why this is not a precise method. Let us look at a weld classification approach. For example, you can see the diagram of British Standard 7608 or similar standards you can refer. Essentially, what it will do is it will calculate the life based on the nominal stress range. So essentially what it does is display the life in terms of cycle, mainly as a function of normal stress range, and it will be subdivided into different categories for different weld classes. So the way this works is that you need to understand and know what your geometry is going to look like, and find the correct weld class. For example, in the picture as seen in your window, it is a class F2. So based on the graph, you can find out the life based on these nominal stress calculations. So that is one approach. Another similar approach is suggested by IAW. This assumes that can be shifted up and down. Basically, you go and based on your load definition and work out what kind of fatigue class you are using. Then you can go into this diagram with the nominal stress range or even hotspot stress range and try to work out what your fatigue life is. The British Standard 7608 is included with the basic license of your FESAfe and uses normal stress in critical plane searching manner. But if you want to develop something new and more robust, then we need to put some demands on it. It needs to be consistent in calculation. That means that it needs to be very well set up in terms of machine insensitivity, and also we need a very high degree of effectiveness when it comes to SN data correlation. And similarly, if it is a single master SN curve, it will be great, which is applicable for different joint geometries or plate thicknesses and so on. VERITY in FESAfe. The VERITY is a mesh insensitive structural stress method, and it has been developed and patented by Battle Institute in Columbus, Ohio, US. And back in 2005, CF Technology and Battle collaborated together to bring to the market the first available structural stress method for the fatigue of welded joints. And VERITY in fesafe remains the only commercially available version of the original method. It was developed in collaboration with the leading engineering companies who are members of Battle's joint industry project. This allowed the method to be thoroughly validated on over 3,500 welded joints. It's this testing and validation that really sets it apart from other softwares. It is machine sensitive and it can be applied to all kind of welds. Be they structural welds, or it may be seam welds, or spot welds, or solder joints, and all the thickness of the sheets and plates. When there is a continuous development of the VERITY method, which has led to a release of fast and automated approach to spot weld fatigue. And when it comes to a typical industrial application, automotive and ground vehicle chassis and bodies of off-highway machineries, and pressure vessel, piping, rail bogies, and carriages are the main application areas for this fesafe VERITY. So what stress should we use? This is the definition of a structural stress. If you look at the actual stress state of a welded joint, you can basically decompose it into two separate components, which we term structural stress and notch stress. Summarizing these two use the actual stress state of a joint, and we will look at these two stresses separately. A little more precursory information here. There are some things we need to consider when dealing with numerical implementations. One is that most reliable quantities you can get from a finite element procedure are the nodal forces and also the displacement. So because the equilibrium condition are always going to be guaranteed, that's what you want to be working with. Now the equilibrium equivalent structural stresses can then be extracted using nodal force in abacus and something similar in other tools. Then we are going to apply a work equivalent based on work equivalent based mapping to turn the nodal forces and moments into line forces and line moments. So this is the way that works. There's a schematic of a weld line on the right hand side where you can see a big black line showing the weld curving, dots at the nodes and the grid lines in the elements. There is a local coordinate system generated at the start node and transformed along the weld line as there is a curvy structure. Essentially, the method needs to track its way along these nodes and work out a system so that you basically have the nodal force vector on the left and the geometry at the center, and then this is used to convert the excuse me. Then it is used to convert the nodal forces to line forces and line moments. Then based on these you can calculate your structural stresses. What about mesh insensitivity? Let's go back to the hotspot example from the very beginning of this particular webinar. This structure is an example we can use to demonstrate what VERITY will do. when it comes to mesh insensitivity. We have a couple of different meshes here. And the key feature here is that you can look at it, the stresses are developed along the path going from initialized point, which is where the dashed line AA cuts the cross section, and it moves around the circular geometry in the center. This has been analyzed with VERITY using two different mesh refinements. As you can see, from half of the thickness of the plate, it is having one is a very fine and another a very coarse mesh. You can see it, and here is the result. If you look at the normalized structural stress, which we have at the vertical axis, this is the result. You have the distance along weld toe on the horizontal axis, and you can see that how mesh insensitive the fesafe VERITY is. There is a very good correlation between when for a coarse mesh as well as very refined mesh. So it is mesh insensitive. So let us take one more example. This is A.SAE's Weld Challenge 1 example. The tubes are welded together, and a load is applied at a certain distance from the center of the tube. Okay, and it will cause a bending moment type of load. If we try to find the location of the crack, and we are using three different type of models here, again, two with the solid meshing and one with the shell meshing. The impressive feature here is the structural stress, as it varies over the distance from weld and attachment site. The highest structural stress is identified at the correct location on all the three models, as you can see. Again, it doesn't matter what kind of element or what kind of refinement we are using when it comes to meshing. And one more interesting thing here is that actual failure location is also exactly wherever the fesafe VERITY predicted it. So this is where the whole story of notch stress comes into play. If we go back to the description from the beginning, we have actual stress state at a joint, and we have decomposed it so that we have the structural stress and the self-equilibrating notch stress. This is what we want to describe. We will show on the next slide self-equilibrating stress using fracture mechanics approach. So we now have a formulation of a fracture mechanics based equivalent structural stress parameter, or delta S. This consists basically of three main components. One is a stress concentration effect, then we have a thickness effect, and multiply by a loading effect or loading function. Here we have R, which is a ratio of membrane stress and membrane stress to that of the total stress of the system. So which SN curve to use? So essentially now we have developed a method to calculate stress. Now let us look at how it performs. These are just a few selected geometries, different geometries you can see, and even weld types and different loads are also you can see. This has been a few cases which has been investigated by Battle University. The joint type shown in the upper right is for the steel with plate thickness varying from 10 to 90 mm. They include the bending and axial loads, and if you take these results, you can you calculate the nominal stress range and you plot it versus the amount of cycles until fracture or crack initiation. Then you will end up with quite a scatter. You can see in that upper left hand side. If we apply the stress range, you can see that the stress points start to collapse neatly on the line. You can see that in lower left. Here the question is, can we make it slightly more precise? The answer is yes. We can do that by using equivalent structural stress range versus the amount of cycles to crack initiation. You can see that all the test values collapse very nicely onto one single alignment. You can see that in the right hand side, lower right hand side, and this gives what we want. We now have a master curve for all the material or families of materials, and also FECF includes these scatter for calculating the fatigue life of any component. Here is a typical Lap-Weld joint failures. Mainly there will be three different types of failures: toe failure, here, root failure, as you can see here, and throat failure. And all these type of failures can be accommodated in FECF. And I have given one example here. As we have seen from the formulation that even geometry as well as loading is required, and FECF will calculate the structural stresses and it will calculate the fatigue. So as a part of model building, we need to define a few things in your FE model itself. For example, if it is in element domain, what you need to do is for say weld toe type of analysis, you have to define your welded structure, which is in red color, and toe structure where you want to analyze. So you have to keep it in a different elemental group as well as nodal group you need to create. And similarly, you need to know what is the starting point or starting node and starting element. These things need to be manually done in FECF, and fatigue analysis can be computed. A few more interesting options we have included in the recent release, where for a solid weld definition, there is automatically it can find the weld. There is an automatic weld finder option. Here you need not do any extra work when it comes to FECF VERITY, but again you have to define these elemental groups wherever you want to do fatigue analysis of weld. Weld groups need to be defined separately, and all other things FECF will do by itself. Let us go a step further and look at a simplified procedure for spot welds using structural stress method. The conventional structural stress method is very reliable, but it has a downside. It requires it requires you to model the weld nugget using your finite elements. This takes time, and it's a bit of a bother. If you have a few spot weld, it doesn't matter. But if you are looking for something like a unibody where thousands of spot welds are there, it is going to be a big headache. So there is a simplified modeling procedure available for these type of spot welds. And if you are using a preprocessor in Abacus or Nastran, you can use a simple one-dimensional beam element. And if you are using Abacus, you can also use point-based or discrete connectors and fasteners. This greatly reduces the modeling effort, and also it will speed up your analysis without costing you in accuracy. If we look at the conventional model, as you can see, you need to model the element in a washer configuration around your nugget, and you need to combine them with multiple point constraints, and in this case you can say a rigid beam, so that the planes are related together or combined together. A simplified model has not only made the size of the model very less, but also more efficient when it comes to speed as well as accuracy. Now let us compare how ascent curve can be collapsed using both the conventional and simplified model. Again, we are going back to the example of trying to plot nominal stress range, and we can see that there is no real possibility of making everything collapse on a single line. But there's quite a bit of scatter is always there. And if you use conventional model, you can see that everything lies very neatly on the line, and the scatter is very small. The same is actually true for the simplified model also. And either of these are entirely adequate to do more than it can replace the conventional model. One industry application example is here for the simplified spot weld procedure mainly. This is a courtesy of Hyundai Automotive, who's using this particular tool, and they are using a quasi-static method and the modal superposition method. We are not always getting the precise results, but the feedback from Hyundai is always been that they are very pleased with how the code is working. That's what they are claiming. Let us understand the application. What is the range of application? You can see from this particular slide, and Batley is still researching topics from root failure to thermal to improvement technique, a few improvement techniques for weld. And you can see the list goes on, and it is a robust computational scheme. Here is a discussion of industry range mainly. All of these industries have one fundamental thing in common. They need to look at and keep up with the issues related to weld fatigue. They are under significant demand for precision and mainly for safety. Here I have a example. This example comes from Ford. They conducted a few investigation on different components. This is the example from Ford. They have conducted few investigation on different components, and this is a rear trailing arm link, and rear trailing arm link of one of their rear suspensions. Okay. The test result to crack initiation was the nearly 0.83 repeats, and this is found from mainly test results, and VERITY predicted nearly 0.81 repeats, and these don't go by the word 0.81. These tests will consist of many events stitched together in a long run, and it's very complex loading definition. So you can see that there's a very good correlation between the test as well as simulation. This example I want to show is coming from Equity Engineers Group, and they were looking at a weld in petrochemical sieve vessel. As input data, they used a transient thermomechanical finite element analysis, and their aim was to try to predict the fatigue life as it occurs exactly in the field. And FSA predicted nearly 75,000 cycles, and it was in very good agreement with the actual field failure. They also ran the A.SAE best fit approach, which predicted nearly 240% longer life than fesafe as well as even a test result. The next case study is into the spot welds. This example comes from a leading automotive OEM, and it's analysis of a automotive body. Here it is nearly 27,000 analysis items have been analyzed, and the size of the file, result file mainly, is nearly 1.2 GB. And road load data is applied by scale and combine loading for nearly 48 different load blocks. So 48 different events, each having 24 superimposed load histories. So the analysis was solved on an off-track workstation, and time, as you can see, it is very small. Even for a whole body, within 12 hours, it's solved in a small system. Here is my final example. This explores mainly whether we can whether we should use seam weld or spot weld. This example comes from mainly Simulia, and there is a lot of confidentiality related to this particular slide. And I do not know what exactly is the actual application also. But the aim here is to try and find sensitivity towards what kind of weld you can use in this particular structure. It's a very complex structure, and the load profile being applied is very complex again. And feedback we have been getting is that this type of sensitivity study use precisely the feedback that it is required by the client. So here is one demo problem. This is a very same problem which was done by fesafe VERITY in a A.SAE weld fatigue life challenge. I'm launching my fesafe window. I'll clear all the previous settings. For the benefit of those who are joined newly for today's event, I'd like to explain that fesafe is having mainly 5 windows, 3 input windows, and a integration window and message window. So 3 inputs are like FE results from a current FE model we will take. Material database is available. Here we will assign our material, and we have a loaded, if you have a road load data kind of file, you can take it from, you can import it in loaded data file. And these 3 things will be integrated in fatigue from FE window, and you will analyze here. If there is any warnings or errors or any other message will be popped up in message log. So I'm going to open the FE model here. This is a solid tube model. I'm rescanning this particular model. As I mentioned in my webinar, one of the requirement from your FE solver is the forces. So you need to import the forces to find out the structural stresses. So I'm importing that forces here. Here my model, FE model is in PSI, force in LBF, and it's in inches. So I will give the respective units and we'll click on OK. Now it is asking for edit group list. I'll give yes. I will move everything here, and only parts I will import. I will give OK now. We have fesafe VERITY coming in as a plugin. You can see VERITY here. I will click on VERITY, define and analyze weld geometry. Weld definition window will pop up. I will click on add legacy line definition. These are the information we need to upload here. My model is a solid model. It's not a shell model, so I will change shell to solid from the drop down list. Plate thickness is mainly 0.312 all these details you need to have it beforehand from the FE analysis. Reference normal should be decided based on your orientation in FE model. So for my case, it will be 0, 0 and -1. I have noted down my start element as well as start nodes also. My start element is element number 76, whereas start node is 354. Again, your weld line need to be defined in your FE analysis itself. So I have defined it like entity node. I will click OK. Similarly, you need to define your weld reference elements or elemental group also need to be defined. We are doing a toe analysis here. I'm selecting T toe here. I will click on OK. So I have defined almost all the parameters, and you should have these parameters handy before you start your fatigue analysis, and all these data are available from your FE analysis. Once I give all these details, I will click on Save and Analyze. You can see that it has created a structural stress dataset. I will close this view, and you can also see that it has created a VERITY subgroup. So for analysis sake, I will keep only this particular window, and all other window I will give don't analyze. It will save my time. I'm doing this only for the demonstration purpose. We are only going to analyze our welded structure. If you want to study only about your welded structure, you can do not analyze for all the other subgroups. It will enable you to only keep your VERITY, and loading I have defined here as 1 - 1. It varies sinusoidally. With this, I will give the output location, and I'll give analyze. You can see that worst life repeat for that simple sinusoidal load in the welded structure is nearly 3 lakh cycles, and it is in element 15 and node number 5. I will open my result folder now, and we will check the result. You can see that FESAFE has solved only for the welded structure. That also welded structures toe we have analyzed, and we have results only for the toe elements. You can see the lowest life here. We can post process only T2 where we have the results. You can see here, this is the lowest life region. So if you remove these particular elements, you can find the next lowest elements. Remove these three nodes, these three elements. Next lowest is this. Similarly, you can find out life in any of your critical regions. For instance, if this is your critical instance, you can go and search for can search for individual elements. You can see that log life repeats. You can see that for element wise. Nodal results are also available, and at a particular location you can find out the life. So this is how we do the fatigue life prediction using fesafe. Let us summarize today's webinar. So we have understood that fesafe VERITY approach is a mesh insensitive approach, and that's very important point. And it works for describing the fatigue behavior of welded joints without being overly complex. And this makes it easy to use an automation mechanism for any complex structure. It uses mainly a unified fatigue damage parameter, and it's therefore possible to use independent. It's mainly independent of geometry or loading direction or any and so on. And that's exactly what industry like oil and gas and other industrial segments are looking for. They want something robust, and also the fesafe VERITY method has been extensively validated, and more than 3,000 or 3,500 test cases have been validated back from 1947. So this is about fesafe VERITY, and you can ask your questions.